Good morning, everyone. Thank you for being here today. We are excited to present our project on the real-time gate traffic counting system. This research was conducted by Churasa Chern, Panuwasibang, and Theopong Theosat from Rasima Vialai School. Our work was supervised by Dr. Suret Tantrarat and Mr. Pamon Khenkam from Sorali University of Technology. To give you an overview, our presentation is divided into 5 main sections. We will start with the introduction, where we discuss the traffic congestion problems and our proposed solution. Next, we will go through methodology, explaining how we collected data, trained our AI model, and implemented the tracking system. Then we will present our results, showcasing the system's performance and accuracy. This will be followed by a discussion where we analyze the challenges and improvements. Finally, we will conclude with application and acknowledgement of supporting for this research. Traffic congestion comes from two main problems: increased traffic volume and poor management. More vehicles mean more pressure on roads, and when management is ineffective, congestion gets worse. We can control how many cars people drive, but we can improve how traffic is managed. Our project aims to improve traffic management by introducing an automatic vehicle counting system powered by artificial intelligence. The system will use AI to detect, track, and count vehicles in real time, eliminating the need for human monitoring. Our approach is to use computer vision and deep learning, specifically a fine-tuned version of YOLO V11. YOLO, which stands for You Only Look Once, is a fast and efficient object detection model capable of real-time analysis. By training with it real traffic footage, we optimized it to accurately detect and count vehicles in different conditions.
So first up, we collect our CCTV camera footage and we label them using a labeling tool. Then we train the model by feeding the data into the model. And after we get our base model, we will evaluate it to make sure it's solid before we pass it into the tracking and counting system in Python. So let's take a deep look at each step. First, we gather our data from CCTV camera footage from 8 to 9 a.m. and from 4 to 5 p.m. at for entrance and exit. This timing helps us capture a variety of traffic conditions, giving us a more diverse and representative data set. After we get our data, we will use Level4 for labeling. Level4 is basically a tool used to label image, and we go through each image and label them. After labeling, the data will be in this format. It will be a number of class ID, center, center, width, and height. This model tell the model exactly where is it in the image. So after we get our the data, then we will use a high performance environment, specifically Google Colab, to train our model efficiently. By adjusting its hyperparameters, we fine-tune them. So first, we feed the data into the model. It will begin with loss calculations, which calculate how far out the prediction are to the ground truth. And that loss value is sent back into the optimizer, which adjusts the model with, and the updated model goes back into the loop. And this cycle repeats until we get our base model. Next, we will evaluate the model on the validation dataset. It's basically an accuracy test, and we will use a confusion metric to visualize them. In this context, true positive is when the model correctly detects an object. False positive is when the model detects something that isn't there. False negative is when the model missed an object completely. And true negative is when the model correctly ignores the background. Next, we will implement it into the Python as a core framework of the system. We use OpenCV library for video processing and analytics for tracking and counting. So this is how we apply them. First, we use OpenCV to process the footage file, accessing video properties such as frame rate, resolution, and total frame count. We then send each frame into the detection model. After we detect the after we detect an object, we will utilize analytics tracking and counting algorithm to assign a consistent, unique ID across the frame and accurately count the number passing our regions of interest. So that concludes our system, and let's take a look at the result.
We evaluate the model on 4 validation datasets of gate combined gate 4, gate 1, 2, and 4. MAPI 50 was above 0.75 across all sets. Gate 1, 2, 4 showed consistent, strong results. Thought motorcycle detection remain less accurate and needs improvement. Another evaluation matrix we used was the conversion matrix. We test it on 4 datasets of gate combined gate 2, 1, and 4. Calibration accuracy was excellent at all gate 1 and gate 2 above 90%. Gate 4 also performed well exactly for motorcycle, which hit 90%. However, false positives were high across all gates, signaling a clean area for improvement. The result confirmed that AI-based systems can replace manual physical counting with higher accuracy and real-time capability. However, there were some key challenges, particularly class imbalance and misclassification of motorcycle. Improving motorcycle detection will require additional dataset expansion and fine-tuning of YOLO classification layer. In summary, our real-time physical counting system demonstrates a major improvement in detection accuracy and processing efficiency. We achieved MVP at 50 of 0.776 after fine-tuning, and the system runs approximately 100 milliseconds per frame on a CPU. These results show that AI can provide a reliable and scalable solution for traffic monitoring and physical counting. While there are still areas to improve, such as motorcycle detection and hardware optimization, the system is already a strong alternative to traditional manual counting. So finally, we get our real-time gate traffic counting system.
We would like to express our gratitude to SIAS, Suvarnabhumi University of Technology, and Rashima Villai School for supporting this research. This is our reference. Thank you for your attention.